Why does it do that? Okay. So, by writing out this way, you see the advantage. You're after milliliters of KMnO4 solution, so probably just start where? But do what? Flip it. Yeah. So I think you can see what to do. Do it. Right? That's the starting point. Right here. But flip it. Go all the way to milliliters of KMnO4 solution. Keep going. If you get your answer, skip part B. You can work if you want, but I would jump to 7-9. Okay, if you don't have your book, I can scroll up a little bit for you. Okay.
Is B like homework?
B's the same thing. I do the same thing. We were trying to get through as many as we can.
But the ones we don't do our homework?
Yeah. Oh, jeez, it's not even canceling, is it? Shoot. Thank you very much. I don't know why they put those acidic hydrogens on the end, but that's how they did it. That isn't going to work, is it, Daisy? I lost my 1,000. Yeah, we can convert it now, right? What'd you get as an answer? Would have been a lot easier just to write 0.108, wouldn't it? Let's just do what Daisy did. Heck of a lot easier. It's easier to see. Go on to the next one, 7-9 once you get it. 0.04? 0.0432 or something? Okay.
You got that in liters?
Well, the final answer is in milliliters of the KMnO4 solution. No, you did, right? The answer is up here. Oh, you forget you didn't have that one. Oh, yeah. So the answer is 43.2? You can, but I suggest going on to 7-9. I see it's 43.2 is what people are getting on. All right. Suggest going on to B.
So it's 43.2?
Yes.
Well, 0.432 liters, but 43.2. that right? Yeah, 43.2 milliliters. Okay. Try 7-9. Okay. In 7-9, start with what they want. Start with what they want, and that guides all your efforts. Kevin, what do they want? They want you to solve for what? Of what? That molarity of hypobromite. Hypobromite, they say, is OBR negative. Okay, that is really equal to what? Albert, molarity of hypobromite would really be what over what? No molarity. Moles of what? OBR negative divided by liters of that OBR negative solution. Hypobromite solution. So are there any in there that they gave us? We can just plug them in right now. Did they give us either one?
What?
They gave us which one, Kevin? Yeah, how many of them? There you go. They gave us the denominator. Just got to figure out the top. So pretty much just convert what to what, and you'll have it. The milligrams of that ammonia to moles of OBR. I'd say stop here and go on to the next one. If you can see it. If you can't see it, then I would finish it. But if you can see it, go on to the next one. Right? You know how to solve this now. You're going to need a mole bridge. It's there. You're going to need to remember what milli is. What's milli, Javier? 1,000 millis in a hole. Yep. Okay. Did I lose anybody on this one? Yeah, Jesus. Where did we lose you? Do you see where we started? So we started with molarity of OBR.
Right.
And the reason why I started there is otherwise, heck, where do you start?
Yeah,
So I started with what they asked for, and that's what they wanted. They want a molarity of OBR. And that's moles. Molarity of anything is the moles of the stuff or the liters of the stuff. And they told us the liters of the stuff. They said it was 1 milliliter. So that's why somebody converted it to liters right away. 0.001. Now you just got to get moles of OBR. And what everyone needs to get used to seeing is when you're given a reaction, if you're given the amount of anything in that reaction, you can convert it to anything else you want. And the weird thing is given amount, it could be grams of the stuff. Or it could be so many mils of that molarity of the stuff. As long as you know the amount of something in that reaction, you can convert it to anything you want. And that's the situation here. They told us the amount of the ammonia. So we can convert that to this one, to the OBR, by using the mole bridge. Yeah, you're given the periodic table and all those things, so it's fine. Okay. So thank you. Just when I needed it, 17.03. Mole bridge. Right, the final answer, hopefully. Anybody else get that? Oh, good. Okay. Okay. Eustacio, did I lose you? Oh, because they said that's a really weird number, but they said they had 1 mil of the hypobromite. So that's why we knew that this guy right here is 1 milliliter. He's just in the wrong units. He has to be in liters for concentration. So we converted the 1 milliliter to liters. Okay.
I got you.
And now you can plug that into your mold.
Yeah, and then plug it in, divide your moles by your liters. You'll have it. Okay. What's this one? All right. Should we want to go on to this one or save it for? It's kind of the same thing. It's another titration question. I was looking for something different that has a twist to it. Yeah, here. That's okay. Here's a weight percent one. Because the reason why I skipped, just to let you know, the reason why I skipped over this is just another titration question, and it's good practice. But we've done a couple of them already, so you can come back and model after it. But here's a weight percent one. Okay. Let's jump to this one. This is problem 7-15.
Right after 13.
Yes. Solid mixture containing 0.05485 grams contained only ferrous ammonium sulfate and ferrous chloride. The sample was dissolved in 1 molar sulfuric acid. And the iron, ferrous ammonium sulfate. Dissolved in 1 molar sulfuric acid and the iron required to Okay. This is a good one. This was a good one. This one's not going to be on the quiz. It's going to be kind of long. But okay. Weight percent would be what? The grams of the chloride all over the initial grams. Yeah, the grams of that solid stuff. And we know that number. That's that 0.05485 stuff. Okay. Just need the grams of the chloride.
So we can get the grams of the.
Dissolved 1 mole sulfuric acid, iron plus 2 required. 13.39 mils.
We can get the grams of the CD+4 converted to moles and then do a mole bridge to get
Yeah. We can get the total moles of iron plus 2, right? Won't this give us the total moles of iron plus 2?
Yeah, that's what I was thinking. And we would convert it to what? The Fe plus 2?
Okay. Now, let's back up a little. The total moles of Fe plus 2, we need a little relationship here. Total moles of Fe plus 2 would be the moles of Fe plus 2 from, instead of rewriting this whole thing, can I just write a 1 and a 2? right? From number 1, and the number of moles of Fe plus 2 from 2. Are you with me so far? Right? They just threw all that stuff together. Does that make sense? There's 2 sources of the iron. Everybody with me so far? Okay? Okay. So the moles. Now, if we had 0.05485 grams of the stuff, this is with Does this make sense? The moles of Fe plus 2, if you knew the number of grams of the stuff, right, wouldn't you just divide it by the molar mass and you'd get that, right? Does that make sense? That's how we get moles. You divide the number of grams of stuff by the molar mass, and that's how you do it. Do the same for this one. This would be the number of grams of compound 2 divided by the molar mass of compound 2. Okay? Now let me show you. This is really, maybe that's where the trick is. I don't think so. To me, this is where I think the trick is. Let's change colors here. Trick color to green. Let's say, let's let X equal the number of grams of that compound 1, right? So that means that my total moles of Fe plus 2 has to equal X all over the molar mass of compound 1. Let's just put a number in for that. It'll be a lot easier. Well, we'll write it again, and then you'll see. Let's make our big plan. Molar mass of compound 1 plus. Well, if X is the mass of compound 1, what's the mass of compound 2? Remember the trick? They said,
total minus compound 1.
yeah, it only contains those 2. So if I take 0.05485 minus X, I'll have the grams of this guy. All over the molar mass of 2. Now, just like any equation, if I only have one equation, I can only have one variable. X is definitely a variable. Do we know the molar mass of number 1?
Yeah.
Yeah, you just have to add it up. It's going to be some work. We'll let Andrew do it. Do we know the molar mass of number 2? Yeah, again, it's just a chemical formula. You figure it out.
It's right up there anyway.
Do we know the total moles of iron? All right? They told us. Remember I told you, it's just something you have to get used to. If you're given a chemical equation, and if you're given the amount of one of them, you know the amount of any of them. And amounts can be given to you in easy ways, grams of cesium-4, or they can be given to you in hard ways. 13.39 mils of 0.01234 molar cesium-4. You know the amount. Just multiply the 2 together, and you have the amount. So, does that make sense? Right here, you are given the moles of cesium-4. You know this one. Big deal. Great. We'll use the mole bridge to get the moles of this one. So we know the total moles of iron 2. We'll be able to solve this. Okay? Okay. So I don't think we need to go through it. The rest is just plug and chug, but make sure you can see how to get this. Okay? So where did I start? They said, hey, what's the weight percent? Okay, well, that's just grams of what they're after over the grams of the solid. Oh, I forgot times 100, right? And then here's from the titration data. The total moles of iron, I could just scribble 13.39 mils of 0.01234 molar cesium-4. That's what this will be. Okay.
So you don't have to do those calculations with it?
Well, you're going to have to do this to and do the mole bridge and see what that number is.
But like those 1 plus 2.
Oh, and then you kind of just jump down to this guy,
So we don't
right?
Yeah, we can
Just
figure
jump right down to here. Put that number right in here and put in the molar masses, and you'll have to solve for your x. And once you solve for your x,
X.
they're interested in chloride, so get, here's your, let's see, number 2 is this one. So we'll know the number of grams of it, so just convert the number of grams of this into grams of chloride. So first convert it to moles, then I can write your final step in case you don't see it. So boom, 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 a lot of work. And you get 0.05485 grams minus x equals the grams. They call it what? Iron chloride, what is that, 6 hydrate or something? 6 hydrates? Okay. So then what you need to do is a final step. All right. Final step. Start with those grams of FeCl2 6-hydrate. The molar mass of it, which you already know because you had it figured out earlier. All right, the same number as this guy. That's that. And then in 1 mole of this compound, how many moles of Cl negative do you have? The formula tells you. 2 of them, right? Yeah. It's kind of like, how did you find the molar mass of this compound? 1 iron, 2 chlorines, 12 hydrogens, and 6 oxygens. So, well, 2 chlorines. So for every one of those, I have 2 of those. And then the molar mass of chloride, and you'd have it. And that will be your grams of chloride. And that's what you finally put in way up at the top, right? Okay. That won't be your quiz, but it could be on the test.
So
right?
then, okay, but then like, can we go back to the very top?
Yeah.
You were talking about the number of grams for number 1, number of grams for number 2.
Yeah.
And so,
I guess the trick to realizing that is they said all it contained is number 1 and number 2. So if we say let x be number 1, well then the total minus x has to be number 2. And that's all we're doing. We're saying x is the grams of number 1, so then the total minus x has to be number 2. Because they told us that total mass.
So
Right.
from that step right about total moles, we take that straight down and plug it in for total moles.
Mm-hmm.
Plus,
So this will be a number.
and then just solve, we're going to have x, and we're going to plug in the moles.
Yeah, x over a number plus this minus x over a number. I would probably see what those 2 numbers are, multiply through the whole thing by them.
That's right up there, right?
Yeah, it has to be the molar mass of them. You have to add it up.
But it's written there, right?
Oh, it is? Oh, it is! I didn't even notice that. Thank you. We could have done that. I mean, it saved a lot of writing. This one's 329.13. Oh, I wish I would have seen that. And the other one's 234.84. That's why I did this whole 1 and 2 things. I didn't want to.
Yeah.
What did I say? 234.84. All right. And then you'll get this number here. But what's the easiest way to simplify this?
Multiply by both the denominators.
Yeah, good. You see what Eric said? Multiply through both sides by both of these, right? So like the 329.13 will cancel here, but you'll have a 234.84 times x. Here, you'll have this quantity, 0.05485 minus x, times 329.13. And then on the product side, on the total moles of iron plus 2, multiply it by both denominators.
Or you could just say it like, find common denominator on this side.
Or since you have a calculator, why even mess with it? Just divide 1 by that number, right? Divide this by that. Divide -1 by that. Might even be easier, since we have calculators. Okay. All right. So you can. Let's try this one. Yeah, Matt.
I think by making it easier, I think I just got it. Yeah, I think it made it harder, much more make it easier. Can we maybe like do one where we actually like look at kind of like all the way through? Because
Well, I want to touch on. Yeah, you can spend all the time on YouTube looking at that, and I'll be glad to work it out with you. Right? Let's do this one all the way through. Okay. Because in my view, Matt, setting these up is the hardest part. The rest is the math. And if you need help with the math, you got to come in so I can help you individually. But just setting it up is the hardest part. I really strongly believe that. So let's try to set this one up. Let's try to set this one up. Okay. Calculate the molarity of cyanide in the 12.73 mil cyanide sample. Okay? So if they want concentration of cyanide, that's where I would start. And didn't they tell us half of it already? 12.73. There you go. Half of it's done. Okay, now we did one of these, we did this a couple times, this type of question, a couple times in lab. We did these problematic lab problems. Do you remember the trick? It was a lot easier to do an analysis this way, where they said you just add excess, add a whole bunch, right? Get it all to react.
Like the moles in the first and the moles in the excess. Subtract the excess moles.
That's it, right? So we'll have a total moles. Right? In this case, we're talking not about carbonate, but we're talking about or hydrogen. No, it was with acid, with H+. Here they're talking about nickel, because that's where we added this excess. So we added some total moles of it, right? And that has to equal the moles of nickel that reacted with what we're interested in the first place, right? And that's the cyanide. Right? And then that leftover nickel was reacted with what? What did it say? Reacted with, yeah, EDTA, ethyl diamine tetraacetic acid. I'll just say moles Ni plus 2 that reacted with EDTA. Okay? You see, does that make sense? So we're after the moles of nickel that reacted with the cyanide, because then we can figure out the moles of cyanide, and then we can put it up into our answer. We just need to get both of these. Okay. Now, yeah, we have to look at these solutions. How about let's start with this one. How do you get this one? Do you see the titration data to get it?
It's the excess that does not react.
It's the excess one, right? The 10.15 mils of, right? You're going to use this to get it. Use to get, right? And you're starting with EDTA, so you're going to have to use a mole bridge to get there. But they gave you the reaction. We got to have this one. And we'll work it out, right? Make Matt, right? Matt will work the whole thing out. Yay! Okay, now we got to get this one. Usually in those questions, they tell you the concentration of the stuff. You know, you're dumping it in excess. You think you'd know what the concentration is. But they said, no, you got to figure it out. You see that at the very end? Right here. Let's make that a different color here. You got to figure it out. If 39.35 mils of EDTA were required to react with 30.1 mils of the original nickel, then calculate the molarity. Let's see.
That's for the.
Oh, that's the wrong one. 39.3.
We're looking at that excess, right?
Let's see. What does it say? Oh, 25 mils of the nickel. Here's 25 mils of the nickel. Okay, so we will have 25 mils of this stuff. Oh, I thought they did another titration. They didn't. We got to look at this. We're required to react with 30.1 mils of that original nickel solution. Okay. Okay. Do they give us? Yeah, here it is right here. They gave us the concentration of the nickel.
Isn't it just like that moles minus excess moles?
So use this and this. You can get the concentration of the nickel, right? Because what is the concentration of nickel? What is concentration of nickel? Big M, Ni plus 2. It will be moles of Ni plus 2 all over the volume of Ni plus 2, liters of Ni plus 2. Okay? So they said 39.35 mils of EDTA. So right here, the moles of the nickel you can get. That's 39.35 mils of that. What was the concentration of EDTA? 0.01307. Oh my goodness. 0.01307 molar EDTA. Right? Convert that into moles of nickel and you'll have it. Right? And then what's the volume of the nickel? React with 30.1 mils of nickel. Okay, so this is the big game plan. So let's see if you can work it out. Okay? And in the end, we'll solve for this one. So see if you can figure out the two parts I circled here. Get the moles of the nickel that react with EDTA. Okay. Get that with, it's just converting, right, the data. using the mole bridge, and get both parts.
The total moles of Ni plus 2. How did you know where to get that from?
Yeah, how would you get the total moles from this?
Oh, because they took 25 mils. So we need to, I just solved for molarity. How do you get moles if you know molarity?
Just multiply by the volume.
Multiply it by the volume. So once we get this molarity, we'll take it times, what was the volume? 25 mils or something? 25 mils.
Do you have to put it in molarity first to find it?
Yeah, you do. Okay. Well, let's just find it. Let's find the total moles of nickel. Let's find that one first. We'll go from left to right. Okay. So first, find the molarity of the nickel. Just can't write here. First, find the molarity of the nickel. Okay.
So would you just multiply the milliliters times the
Yeah. So we need.
molarity?
Yeah. Well, if it's 1-to-1, is it 1-to-1? Liters. All right. 0.0 liters of EDTA. Yeah, that's right. Times 0.01013. 07 moles of EDTA in a liter. Is EDTA to nickel 1-to-1? Look at the reaction. Yeah, it is, right? 1-to-1? You see that? So it'll be 1-to-1. So we'll have our moles of nickel. 0.03935 times 0.01, let's say 307. About 5.14 times 10 to the negative 4. That's my moles of my nickel. Okay? But to get the concentration of the nickel, gotta divide moles by liters, right? So the concentration of the nickel would be 5.14 times 10 to the negative 4. We use 25 mils. About 0.02, let's carry more digits since they are 0.0206, carry a bunch of digits.
Why did you write 30.10 milliliters of nickel? When you were first trying to solve for the concentration
In the green.
in the degree?
Because, did I write the wrong one? Yeah, thank you, Andrew, right? Because I'm supposed to, we use this volume. That's the volume they took. Thank you, thank you, thank you. Someone's paying attention. Daisy. 0.03010. Yeah, 25 mils, we're going to use that next, all right? 5.14 times 10 to the 4 negative. Divide by 0.0301, about 0.01708 or something. Okay, that's the molarity of the nickel. So the total moles of nickel would be total moles of nickel used would be 0.025 liters times 0.01708 molar. 4.27 or so, I guess. Finally, okay. That was a long one. So now we can plug into our equation. It's kind of a mess up there. I better rewrite it. right? So I'll have 4.27 times 10 to the negative 4. That has to equal, what did we say? The moles of nickel that reacted with cyanide. Okay, write that one. Plus, what did we say? The moles of nickel that reacted with EDTA. And that is all this stuff right here. Clean it up. This guy right here. 10.15. That would be what? 0.01. I already forgot the number. 0.015. 1015. And its concentration was 0.01307. Right? And that was moles of EDTA. Oh, and they're 1-to-1, aren't they? But we can finish it. One mole of nickel for every 1 mole of EDTA. So we'll have the moles of each. We'll solve for the moles of nickel that reacted with the cyanide. All right. Make sense? And then just convert this guy. Once you solve for him, solve for, and that's it, right? Solve for and convert to, because they want concentration of cyanide, right? You need moles of cyanide. You have moles of nickel. See the ratio? They're not, it's not 1-to-1. There's 4 moles of cyanide for every 1 mole of nickel. So convert it to moles of cyanide. Okay. Now, let's just run a few minutes late and finish this completely, right? So we'll have 0.01015 times 0.01307. This number right here is 1.33 times 10 to the negative 4. .27 times 10 to the negative 4. So what's the moles of nickel? No, let's find it. You get about 2.94 times 10 to the negative 4. So start there. 2.94 times 10 to the negative 4 moles of nickel. And 1 mole of nickel, we said there's 4 moles of cyanide. And get your moles of cyanide. .18 times 10 to the negative 3. Final answer. Concentration of cyanide equals 1.18 times 10 to the negative 3. And the volume was 0.01273. Okay. 0.09 molar. Oh, you have to have a quiz next class. Right? So one of these will be on the quiz. We'll turn it in with the when you take the quiz next class. So I'll be glad to work with you on any of these, right?
Which ones are the ones that are like, it's all these, but these aren't in our book, so which ones are they?
These aren't in your book, 4-7-16?
I mean, in our main,
Yeah.
like how are we supposed to, like, it's what?
We'll write them down.
Yeah, it's
Yeah, okay, we have 7-8. There's no chalk. So one of these is your quiz. 7-8. 7-9. 7-13. 7-15. And 7-16. And that's about it, right? Oh, 7-17. Yeah, but 7-18 is not. It's a conceptual. So 7-17. Okay. One of those will be on the quiz.